FCR seminar. Today we have Steven talking about photovoltaics and the Photon-Multiplier.
So some of you guys have noticed I started handing these around. If you didn't get one, you just need to take one white styrofoam ball and one that's covered in tape. And yeah, we'll see. This talk is going to be a little different. I've never given one like this. We're going to try to do some interactive. Let's not call it fun. Let's not go that far yet. Okay, so I want to start by just acknowledging the people I need to thank. Obviously, my entire group at Outdoor Electronics with Catfish. In particular, I will throw one name, Maxime, because he's the guy that basically gets me through my MPhil every day. So thanks to him. If you ever see him, now you know his name. And of course, the Gates Cambridge Trust, which funds me here. Okay, so the aim of this talk is to to spend more time actually trying to learn how solar cells work, photovoltaics. So you should probably learn, this is my outline, not of the talk, but of what you should get. So you should learn how they work, what limits their efficiency, at least the main thing, we'll go over the main thing, and then how we can make them better, and that's where I actually talk about what I do here. Okay, so we already started to pass around some balls and how things are going to kind of work as we do experiments. You guys will be atoms in a material. We'll change the material, I'll tell you what you are. They're not red anymore because I couldn't color them, so the balls that are covered in duct tape, those will be electrons. And light is going to be light. It's going to use. Actually, I wasn't having like a filter wheel, but I don't have that, so I'll just tell you the colors. I'll get into that again. Okay, so what do we know about photovoltaics or solar cells? Basically, we want a way to convert light from the sun, so photons coming in, into electrons. So the photons obviously come from the sun. I don't know, maybe people know, but this is like a question I was thinking of, where do the electrons come from exactly? Where are they generated from? So we're going to go into that. The answer obviously is quantum physics, like always. So it's going to be really basic, so don't get scared. In fact, most of you hopefully have seen this kind of particle in the box, sort of one atom description of the energy levels in, people have seen this. Basically what you need to know is that when you have an electron in an atom, it can't just have whatever energy it wants. It can only take certain discrete values, right? We're all familiar with this concept, so it could be this energy or that energy, not that. Okay. So now let's move up in the world, and now we're a molecule, and we have several atoms. So as you might imagine, we have more permittable states, more permittable energies for the electron to be at. Some people maybe are familiar with molecular orbital theory, right? This is like the idea behind that. You fill up these levels with electrons. Okay, same thing, you can have them there. Okay, so now let's add more atoms, and more atoms, and more atoms, until you get to like bulk material, like everything we interact with every day. And you form these things called basically energy bands. These are full bands of permittable places for the electrons. So basically, any one of these energies, an electron could be in here, just not in this middle sort of gap. Okay. This is like the important concept that we're building up to. It seems a little hand-wavy, right? We just added more lines, but there's actually like solid theory on let's put a bunch of atoms and calculate what energies they can have if we have like an infinite like line of atoms. And you get this is what you get. You can get that basically in bulk materials. You have these energy bands of permissible energies for the electrons. So right now, you're a group of people, and you have your atoms, and they can only be at certain energies. This is important because we can classify different materials by their energy bands, basically, or sometimes called the energy landscape. It changes as a function of other things as well. But this is the most basic, and what you basically need to know is that big three subsections of materials based on the electrical properties are metals, which conduct electricity really well, and that's what their band diagram looks like. And actually, you have an overlap between this, what we like to call the valence band, which is the bottom one, and the top one, which is the conduction band. It's synonymous to, if you know molecular orbital theory, like the HOMO-LUMO, the lowest unoccupied molecular orbital and the highest occupied molecular orbital. Or if you're just thinking of one atom, this is like the valence band, the outermost shell of atoms. And then this band is empty. but potentially you could raise an electron's energy state to that band. So now the only difference here is kind of a blurry line, but you have insulators which don't conduct, like this wood and stuff, and they have large band gaps. So basically it's hard for electrons to go up into this conduction band because electrons that are in the conduction band conduct electricity. And then the middle one, which is semiconductors, which are really important to photovoltaics and the talk I'm giving today, and they're somewhere in the middle. They have this band gap that's smaller. Usually what people classify it as is that it's just enough energy so that at like room temperature or thermal energy is enough to move some electrons up into this gap sometimes, but not a lot. Anyway, let's keep going. Okay, so the experiments I promised. Here's some quick things you need to know. It's going to be on the next slide too, but we're going to do some experiments with different colors light, and these are the energies of light. So just think 1, 2, 3. So like 3 high energy, 1 low energy. All right, everyone's okay. So now you are a material with this band gap. You are a material with a band gap of 2, and okay. So also to give you a little more information, you're kind of in this full band of, the valence band is full of electrons. You're here at the top, and there's a conduction band that's empty. Now I'm not going to tell you a lot. I'm just going to let you see what you guys do. See what happens. And I'm just going to tell you that right now I'm shining red light on you guys. So you have your electrons in your hand, and I'm shining red light.
Just the tape cover.
Yeah, just the tape cover. Okay, let's start with something before. I'm going to shine green light on you guys. Yeah. Okay, cool. Green light. Yeah, it's fun. Okay, most people got it. It's pretty easy.
What am I doing?
Yeah, I don't know. Why you have your
Am I
hand up?
supposed to move the little thing?
Yeah, you're supposed to move it. Yeah, okay, so
I'm supposed to show you by the height where I put it.
yeah, a
or
little
in
bit,
the
yeah.
display or something.
Exactly, yeah. Okay. Yeah.
So originally we are in the right band. So where here so we have one EV.
Now.
No. Actually, it's not important what energy you have right now. It's just important how much energy you're receiving. So that's a good question.
Okay, so you are giving us good light.
Yeah.
And our energy increased by 2.
Yeah.
And what's this mean?
That means your energy increased. You're just telling me and everyone else that your energy is increasing.
Okay.
Or how about this? Maybe this makes more sense. I've never done this. How about if you put your hand up, you're in the conduction band now. Let's just worry about if you're in the valence band or in the conduction band. Okay, so red light. Right, nothing happens. Green light. You have enough energy now to jump this gap. Okay, and blue light. Any really quick?
It's not look like anymore.
Okay, yeah. I was hoping people would stand up. Okay. Oh, no.
No.
Get up. Yeah.
I will put it down. I will raise it for blue light.
Yeah, exactly, blue light. But, so blue light, so this is a good point, is more than enough energy. So where exactly are you here? 2 is enough to get to here.
Top of the band.
3 would maybe put you somewhere higher, right? Okay. Anyway, let's keep moving. Let's keep moving. Now you're a different material, and your band gap is 0.9. Okay, so it should be pretty easy. Red light, and blue light, and green light. Perfect. Hey, this is, if I just started with band gaps later, we'd be confused. So one more, just for absolute certainty. You're a 3.1 band gap material. Okay. Now, red light, green light, red light, blue light. Okay, we get it. You don't have enough energy from the light I'm shining on you to increase the electron. For the electron to, even if you give the electron 3 eV, it can't absorb it. It can't take it in because it's not enough to jump to another state. Like when we had the one atom picture, if I gave the electron energy, but it wasn't enough to go to the next level, it would just do nothing. It wouldn't be able to absorb that energy. So basically, you can absorb the light when it's enough to jump this. Otherwise, the light just passes through. You can't do anything with it. Okay, good. Okay. So now you're asking yourself, what the heck are holes? And that's a great question. Holes are quasi-particles of positive charge. We say they're left behind when you excite an electron up. Okay, so confused faces, good. Because now we're going into the online assisted section of this talk, where I copped out, and there's great animations online on this website called PV Education, and I think just a breeze to go through a lot of material to cover solar cells. It helps if I went through here and just filled some important slides. Okay, so you basically did this. You were an electron, and I gave you energy from something. We're going to use light.
Can you zoom in?
Probably if I was smart. My laptop's
Up the right corner. The 3 bars. 3 bars.
Uh-huh.
Yeah. Zoom in.
Control plus.
Oh, this is okay. How about that? Kind of good? Can I see? Okay, so now you're this electron here. What's important is this gap that's left behind. So now there's an electron missing from the bottom. Okay? And what can happen to that missing space is it can move around. This thing says it's moving around like air bubbles in water. You could think of it that way. But basically, these atoms could shift now and there's this gap. Okay, and this gap is it's much easier to think of it as just its own particle. Even though it's no particle there, it's easy to think of it as just a particle with positive charge. And that's called a hole, right? It makes sense. There's an electron there, now there's a hole there. And so oftentimes they're always in pairs. So every time you excite an electron, people say you make an electron hole pair. Okay. That's all we need to know there. Yeah, good. Okay. Let's talk about doping. So how do we have, okay, we're going to talk about different types of semiconducting materials. So there's basically 2 types. There's one for semiconductors that have holes and one that have electrons. So basically what happens is when you have a lot of these excited electrons, then you're left with you're left with the atom that's missing an electron, so it has a positive charge on it. So this is like the nucleus has a positive charge, and there's all these electrons floating around. And you could have the same thing happen, but instead do it with holes. Okay. Good. So what's confusing here is like, okay, what does the material look like? Why does it have just electrons buzzing around, and why does it have ionized nuclei? And so what's a common way to do is you take a material like silicon that has 4 valence electrons, right? So you see it's these 4 bonds to each other, and you just stick in another atom that has 5 valence electrons. So it makes the 4 bonds with the other ones, and now you have like an extra electron floating around. And so that's what's happening here, is you're adding these doping materials. And for the whole doped one, you just do the opposite. You put like a material that has 3 electrons in its valence shell, and when you mix it with all the silicon, which has 4, then it's like it's missing one. Right? So you have these P and N type semiconductors. Okay, now what? Is there one thing before? Okay, yeah, so now we want to people make these materials, they discover the materials, what do we do with them? Let's smash them together. Okay, so can we do this? Can we think of an experiment here? I want to do, okay, so now imagine we have put these P and N type materials together and we have this imaginary order. So they're kind of like not connected. Let's divide the room here. Let's just see what happens. So you guys, you're the P type, and you guys are the N type.
What's P type is with a hole? Or?
Yeah, so your white ball, that one is a hole. I think that's a hole. And so the P type, you guys have holes to move around, and the N type guys, you guys have electrons. And I'm going to remove the barrier. So now the barrier between you guys is removed. So what happens to your holes and electrons? Yeah, you get yeah.
You're an atom, you can't move.
Because you're an atom. You're an atom. So you can atoms can pass their stuff to the ones next to them, generally. Usually throwing doesn't happen. I think.
You mean the atoms that just
Okay,
here, wait, you catch.
Yeah. So basically, you guys got it right. What's that? Is there something you want to say? What happened, maybe? I mean, why did you feel the need to move your electrons?
Minus because you get that.
Oh, that's a good question. So that's called recombination, and but I mean, but just because, yeah, so we have to go deeper into like length scale and the Coulombic, like how close they are, whether or not they feel each other. But basically, what's happening, and I'll just reveal it, is that they're just diffusing, right? There's a lot of electrons here. There was pure electrons here. There was pure holes. So they just kind of want to mix. What's happening here, though, is when I remove this barrier, you're a positive core, you're a negative core, right? You're this minus and he's this plus. So what we're setting up here, does anyone know what this is?
A field.
Yeah, it's an electric field, like from physics, when you have positive and negative and it sets up a field. And because these are positive particles and negative particles, they feel force from the field. So they're diffusing, and at the same time, they're feeling this force. That's just what happens when you stick them together. This is like the solar cell, basically. You just put this together, and you hook up some wires to it, and that basically works as a solar cell. So that's what's going on inside. Okay, you guys really want, I think, what you really want to see is just a solar cell, how it works. Let's just go. So, here we go. Boom, right? Solar cell, what did I tell you? Just N and P and then some electrodes and you're done.
Steve, why is the P area so much bigger than
That is a good question.
It could
There's-
be for illustrative purposes.
Yes, I don't want to give a totally bullshitty answer, but there's lots of reasons. One could be that your N material is what absorbs really well.
Right.
And so, or it doesn't, right? I mean, in this case, the N material is the one that absorbed the photon, right?
Mm-hmm.
Yeah, let's just not get into now. But let's save that question. It's a good question. There's lots of good directions to go there. Okay, so you had your light come in, and you created a pair, right? You excited an electron, and now you have electron and a hole. And what you want to happen is this electron to go over into one of the contacts. Then you want, the reason for having this NP is to separate the electron in the hole, actually. Because what would happen if you didn't separate them is what you said, is they would just, eventually they would just come back together. And if they come back together, then you can't collect the electron. So this NP, because of the field, it does separate them, right? So the holes want to be in the P side. Right? Anyway, finish animation. You collect an electron. You know how a solar cell works. Just going to check the time. So before you guys to death. Oh, I didn't start my stopwatch. Okay. That means we could just go on forever.
There's a clock.
But
so.
this is all I have. This is like the end of solar cells. So I think it's the basic operation, right? It makes sense. Light comes in, you generate an electron hole pair, and then you separate it with the NP junction and you collect the electron in this current and they recombine at the other end. Right? Okay, good. Let's go back to my slides. Yeah, so we went over those things. Okay, I wonder what's next. Okay, we have to talk about this one. Does everyone know what a black body is? No, good, I'll tell you. Okay. Basically, black body radiation is the radiation that you generate just from having a temperature. So like we saw those, when an electron and a hole combine, they emit a photon of light. Okay, I'm telling you that. That's what happens. So when you heat things up really, really, really hot, you give the electrons in the material enough energy to jump to higher bands. So like, this is a picture of metal at around 700, 900 Celsius, I think is when it glows red. So that you're seeing red light from just basically a piece of metal. And it's because the metal's so hot that even though, remember that earlier picture with the bands overlapping? You're getting it so hot that it's jumping to even higher bands. So there's other bands up here that electrons usually don't go to, but You give it so much heat that they jump up there, and then when they come back down, then when they make transitions, they emit light. Okay, so this is basically the sun. You just have to think of it as a really, really hot thing. So the sun's about 600 Kelvin, and 6,000. 6,000. Oh, people are awake. Okay, and what that leads to is like a spectrum like this. So this is the light that comes, the amount of the different energies of light that come from the sun. So I think we're familiar with curves like this, right? There's very little low energy light. There's a lot of visible light, infrared, UV. Okay, good. It's turning off. Oh, no, it's on. Okay. So now we're going to talk about this is the big efficiency sort of thing for you to get, is that we have this valence band, conduction band, right? And remember earlier I shot red light at you guys, and you jumped up here, right? Okay, and then we could absorb an electron like this in our solar cell. That's good. Then I shine blue light on you guys, and you guys kind of like went a little higher, right? So you had more energy. We can't collect any of this excess energy with our solar cell. What happens in most materials is that there's this rapid cooling of the electron. So the electron has high energy, and it just gives that extra energy off to the atoms, basically. It just heats up the cell, and it cools to this edge of the conduction band, and you collect this energy every time, no matter what. And that leads to the basic limit in the equation for the Shockley-Queisser limit, which is like what limits solar cells, is that if you have a material with a certain band gap, anything less than the band gap, you can't absorb at all, so it's worthless. Anything higher than the band gap, you start wasting energy as heat, because you can only collect the energy of the band gap. So here's like a picture of the energy of the light that comes from the sun is this black curve. These are the energies. And here is the energy that you could potentially collect with the silicon solar cell. So silicon has like a band gap of around 1. So 1.1. So everything less, you don't get anything. You just lose it. And everything more, you start to not be able to get any of, all this energy is lost as heat. So this leads to the Shockley-Queisser limit, which basically people want to write down, okay, so what's the ideal band gap? Too big, then I don't absorb any of the light. Too small, and then too much of the energy is lost as heat. And you come up with this easy curve to get, well, maybe not too easy. And this is basically silicon solar cells are 1.1, so somewhere around the peak, right? 33%. It's just the highest we can go based on limitations, right? Okay. I don't feel like something bigger should happen. That's a big thing to understand. It took me a long time to understand how. So like for a single p-n junction like we saw, this is the band gap to pick to get the most energy out of it. And the most energy you could ever possibly get is only 33% if it's perfect. So that's kind of troubling, but okay, let's keep going. So now we're going to move into more what I do. So I came here and I learned about singlet fission. What's that? So electrons have this other property that we haven't described on their in little balls in your hand, and it's called spin. Okay, spin, let's just leave it at that. It's a property of the electron, that's all you know. Some of you might also know the Pauli exclusion principle. Can someone just say it? Just make me happy.
Yeah.
Yeah, this is what?
Well, you can't have two with the same spin and the same phase.
And the same, okay, perfect,
Energy
yes,
is
okay.
blah, blah, blah.
That's going to be important later, perfect. Okay, so people know about, that's like the thing you learn about spin when you learn about spins, you learn the Pauli exclusion principle. Okay, so before we learned about solar cells, we didn't care at all about the spin. Now we do, now the spin is important, okay. Okay, quick bit of history, it's really quick. Singlet fission's not new. It was proved in 1969, like proved, not just discovered. Its interest in use in photovoltaics started around 2004. That's it. Okay, so now we're going to walk through the singlet fission process. Okay, so there are two molecules. I don't know if this will be easier if we go through it and then have two live dummies act it out, or if we do it at the same time. I don't know. You guys, anyway, let's just go through this. Okay, so you have two molecules, and each one of these arrows is an electron now. and the direction of the arrow tells you the spin. All right, so 4 electrons, and we have this new property of each electron called spin, and we're representing it by the direction of the arrow. So light comes in, you guys are really used to that, and it excites one of these electrons, so it goes to a higher state. Okay, now what happens in singlet fission is this guy can go over here, and then at the same time, he comes down here and gives half his energy to this guy, and they do that. Don't ask me why. Don't even try. Why, Stephen? I prepare. Okay. It doesn't. If you don't want to know, it doesn't matter. We'll keep going.
Energy states come from.
Oh, like these guys.
Yes.
Ooh, such a good question. And it's so confusing, and I don't quite understand it because I'm so new to quantum and this world. But they're like always there. So what you're left with is these are triplets. All right, they're not like one electron thing. It's this 2 thing. So you notice they both. This thing has what we call spin 1 because each electron has half a spin. I don't know if that kind of sounds familiar. So if you have 2 that have the same spin in the same direction, they add. So it's like +1 or -1 or something. So these are the triplets. And they just exist as states. And this energy is always there, but you can't. It's hard. Yeah.
Is it always there? Does it only form if both molecules come together? Like form a big molecule?
Like if these molecules
Like
have to be next to each other?
Yeah, like an M2 for example.
M2.
If one molecule is M, then you got an
Yeah, they have to be.
molecule.
They actually have to be really close. So for stuff like this to happen, there's like, okay, so how do these triplets move about? We won't get into it, but it's similar to the way they form, and it's highly related on the separation between molecules. And so I think it's like 10 nanometers. Whereas in other, like in normal, for like a normal singlet, which was just this one, or just the normal excited one, this one can move around like an order of 100 nanometers. It can hop much further. It doesn't have to be close to the other molecules. I don't know if that answers. Yes was the short answer. Molecules have to be close together. Yeah, those are the triplets. They each have spin 1. Okay, so does anyone want to tell me why that can't happen? Max?
Because you have to emit a photon, and photons can only have spin 1.
Okay, yeah, I believe you know more physics than me, but
Also because of the Poly thing.
yeah, I think he was saying the poly thing, but just in a different way. But yeah, I was looking for the answer of the poly thing. That's the answer I was looking for, but that was a good answer. It's because if this one goes down here, well, it can't because these 2 electrons have the same spin, so that cannot happen. Okay, so that's important because, okay, they're emitted, they don't emit light, they're called dark states, the triplets are. And that's important because, consequently, then they exist for a long time.
So, but then they can move apart, or do they still have to stay close together?
They have to stay together. This has to stay together. It exists as like one thing.
Okay.
Yeah. But they could, so the triplets can still diffuse in a way. What you do,
Oh yeah. Okay.
yeah. But it stays together. Good? Yeah. Okay, so they exist for a long time. So that's actually pretty cool because a lot of times in solar cells what limits them is what you mentioned earlier is when they combine again. So even in a perfect solar cell that happens all the time. The electron in the hole, they meet, they combine, and you can't collect it. These can't combine. So they live on the order of, oh, I never figured out. But it's like 100 picoseconds. It's pretty long. Okay, so now let's reformulate the new Shockley-Queisser limit. Now being able to harvest, I guess I never told you what the...
Yeah, what does this have to do with the Shockley-Queisser limit?
Yeah, oh man, okay. So basically, now we have, this is a thing that took 1 photon and made 2 excited states. So before, photons always made 1 excited state, 1 electron in a higher level. Now we have 1 photon makes 2 electrons in a higher level. So that's how we reformulate the Shockley-Queisser limit, because now, instead of the high energy ones that we lost to heat, we just split them into 2 energy states and collect 2 electrons from 1
So
photon.
the energy at dotted line can be like anywhere So it's not.
It depends on your material.
Okay, yeah.
So that was the thing.
But potentially you can, like, if the energy is higher, then you can make dotted line energy is also higher.
Yeah, you can make, by choosing the right material, you could tune this energy. Just like we have materials with all different sorts of band gaps. People try to figure out where these are.
Where are the band gaps in these diagrams?
We're imagining it's this. This is the band gap from the two solid lines. Okay, so earlier I said actually I never said, but what makes something undergo this process, you might ask, in a certain material? Why doesn't it always happen? I didn't give you a particular reason why this doesn't always happen. And it has to do with where this level is. So if this level is roughly half the energy of the band gap, then we find that this process happens really fast in a lot of materials. And also having to do with the structure of material as well. But it actually happens so fast that it outcompetes every other process. So you'll have a material, you shine light on it, and instantly create all triplets. They'll become singlets and then instantly all split. It's actually pretty cool.
Wait, did this live for a really small amount of time? Like, can you?
No, lives for a long time.
Over a long time.
Yeah, maybe picoseconds confused you, but I said long. I said long. I said long time because for you picoseconds is long. Because other things, other processes happen on a much faster time scale. Maybe it's like definitely maybe 100 or. But what was your question?
No, it was.
That was answered.
Yeah, it was answered.
Okay. Anyway, backtracking. So now you could imagine this wasted energy now we could collect by adding some sort of material that undergoes singlet fission. So far they're all organic, so that's why I took this from another slide. And if you do this, so people publish this work, you get this other curve. This curve is not necessarily taking account singlet fission, but more generally anything that you could get is called multi-exciton generation. So anytime you can find a way in your material to create two excited states or more from one photon. And so this is the new limit. So you increase it from 33% to 45. Okay, so that's cool. Okay, let's wrap up. Quickly talking about my project. This part's fast because I know the most about it. Okay, so why is making a solar cell with singlet fission materials not a great idea? Let's move on. So there's one hint. It's the energy of the triplet is half that of the singlet. I never went into what singlet was, but it's just what we started with when the electron first went out. So, okay, hint 2. I knew this would happen, that's why I made it hint 2. And remember that the ideal band gap energy for the highest efficiency from Shockley-Queisser. So remember this value, or this value, the band gap energy, and that the triplet energy is half that of the singlet. And we'll just move on. You guys can think about this. Oh, what? No, I'm sorry.
No, it's good.
I kind of figured no one would answer this, and we'd move on, and it would just stew in your mind, and we'd go back to it later. But this is why don't we just make a solar cell with single fission material and be done? Because we don't. Anyway, how do we actually take advantage of it if we do?
The band gap would be
What's the answer?
0.5 instead of 1? Or would the band gap be
Yeah.
2 instead of 1?
Huh?
So you said that
Yeah, it's
the band
half.
gap, it's half, so it's not 1. So a lot more could change and it would be a lot less stable.
No.
I tried.
Thermal energy is like 40 MeV, so. But is it because you have to have two different materials to take advantage of the open peaks? No.
Jake, your lab is across from mine. You must therefore know. Okay. Anyway, I'll just tell you. So in our group, we don't make solar cells just with singlet fission material as like the N or the P and call it a day. In my project, we're doing this thing, and I like to think of it as like kind of like a sensitizer, and we call it Photon-Multiplier. That'll become blatantly obvious. So once again, we're going to do this little animated thing. So we're going to start with the triplets. So the light already came in. It formed this one pair. And the pair really quickly split into two triplets, and that's them over here. Okay, so now we're going to focus on just one triplet. And So this was the Singlet fission material where the fission happened. And we disperse these, or we want to. Let's just think there's nanoparticles dispersed in our Singlet fission material for some reason. Ooh, we did it. Okay, this triplet eventually finds the nanocrystal here. So these are electrons in the nanocrystal. And this is our triplet, 2 upspin states. And what can happen when they meet is the triplet will transfer from the yellow stuff to the black stuff, like this. So all we had was movement of this electron across here, and that one there. This is the type of energy transfer they undergo when they diffuse. Actually, this when it meets another molecule, this happens. So before we had just like a regular ground state, spin up, spin down, and we just moved it. Now it's over here, and now the triplet is on the black stuff, the nanocrystal. So that's pretty easy. So now it moves there. Now some crazy physics happens again that I tried really hard to understand. But basically, this spin now doesn't really matter anymore. And it has to do with, it's called spin-orbit coupling. And it's because, I feel like you would know, yeah, you would know about the spin-orbit coupling. Maybe later you could give us a lecture. But let's just move on. That spin flips. It flips, now it could go down again, right? Before it wasn't allowed to go down, but now it can. So that's great. It does that. They recombine, it goes down, and now light comes out. And so that's our idea. 1 photon in, 2 photons out. That's it. Okay, so what you do, okay, yeah. Is there time to do this live?
Yes.
Does anyone know why this is I did? So basically now, then we can put something below this that absorbs 2 photons. We doubled the amount of photons. Yeah.
Is it possible?
Yeah, no, yeah,
Can
no.
this satisfy the conservation of energy?
No, yeah, it totally does, yeah, for sure.
Makes the photons have half the energy of the one.
Yes,
Oh,
exactly.
so the energy-
Yeah, so it's like blue light comes in, your high energy light, and then you get 2 lower, like half, like red light comes out.
Is that like the reason why we didn't do just single fission? Because if you just single fission, they don't emit photons because they doesn't come down.
Not necessarily, because you can capture the triplets.
Yeah.
Imagine that you could transfer these electrons to another material. Almost. Okay. So maybe I'll just wrap up and then we can do it live with like the extra time or the question time because I think so this is where my project comes in just really quickly. When we put the nanoparticles in, it's not that beautiful dispersion. They tend to aggregate like this. And it kills this part. When they come together, they take in the photons, or they take in the triplets, but they don't emit light. It's bad. Because there's other ways for them to get rid of the energy when they're together. When they're separate, they're really good at just, or they have no other way to get rid of the energy, so it just waits around until they finally recombine and you get light out. So I'm taking this, I'm making sort of a scaffold, and I'm going to use the scaffold to try to disperse them better. Anyway, that's my project. So far, I made some devices. I showed there was definitely transfer in this really cool, well, I showed it for sure using magnetic measurements, which is cool. Anyway, this is important to know. So the nanoparticles have 3.8% light emitting efficiency. Does anyone know what the light emitting efficiency needs to be for this to be worthwhile?
2.5.
Well, that would be good. Okay, it has to do with this picture.
Greater than 50%.
Yeah, exactly. If it's not 50%, then even though we split the energy, if we don't get at least 1 photon out, then we're doing more harm than good, right? If it's higher than 50%, then we actually get an increase because we get more than 1 photon coming out. So that's kind of like where this is new. Not other people don't do this Photon-Multiplier. It's kind of like a new idea that I get to work on, which is really cool. But there's a big mountain to climb because we're at 4%. It's not worthwhile until we get to 50. And I thought I'd use some data.
So it's 4% when they are joined together, or
It's
even
4% when we make the film. So
like this. Oh.
this is like our excuse for what we think. Okay, so you can make the dots in a solution. They have the PLQE efficiency of like 70%.
Okay.
But when you make films, it goes down to really bad. And we think it's because this is happening.
You think you don't know.
What else
Yeah.
could it be?
Demons.
No, it's probably definitely that. I mean,
Probably.
we're
Nothing else.
so yeah. So when you do experiments like this, you excite the material, and then you look at what light comes out. So right here we have this is the singlet fission material, the green one. On its own is the red one, right? So the red one emits light here, and then the nanocrystals, they emit light here. And when you put them together, the light emission from the organic stuff goes down, and the light emission from the crystals goes up. That's like our proof for transfer. Our like early proof. There's more definitive proof, but basically, what's happening here is that stuff that would emit light here instead is being turned into triplets, getting transferred to the nanocrystals, and then the nanocrystals emit them. That's why you have an increase in the nanocrystal emission and a decrease in the organic. So that's good, we showed that. And yeah, the goal is to understand science and get the PLQE high. Yeah. I spent the most time making the last two. I just want to say thank you. I have fun doing this kind of stuff. I hope I didn't take too much of your time. And I hope you guys have lots of questions. There were even some questions I couldn't answer.
Yeah.
More.
So was the where does the state in the middle of the gap come from question one that is answerable in a reasonable amount of time?
No, because I don't know.
Okay, cool.
I'm sure.
Yeah.
Does it have anything to do with like the later combination of the quantum states from the two separate molecules? Maybe having an intermediate energy?
I don't know. It looks like
It's
I
okay.
didn't.
You're not a theorist.
Atomic. Well. Because when you take two, say, hydrogen atoms and you have like one basis function for each atom, you get sort of two intermediate states when they come close to each other. But it would take a while to explain.
I'm just thinking I really want to try like doing.
Can we do the lab experiment?
Yeah, well, it's like a lot. It's what happens in the Photon-Multiplier. So you guys want it?
Required.
I need like 4 or 5 people, and I'll tell you.
I got
Okay.
Okay.
Cool.
Okay, you could be.
What do I get?
Yeah. This is like what I'm trying to make.
Do I need my
So,
electrons?
yeah.
Oh, sorry. Do I
Okay,
also
so-
need my hole?
Is that the plus minus?
No, let's not. Unless you want.
Well,
Yeah, let's-
no. Do we do the plus minus of the spins?
Okay, can we say that 1 is plus and 1 is minus?
That's
Wait,
top,
do
that's
it
bottom.
this way, so you can be on the camera.
Yeah.
Oh, there's a camera.
I'm pretty
Alright,
It's gonna be the edited, isn't it?
fabulous.
are there more electrons?
I got ionized.
Because how moving?
Do we?
I got as about as many as I
think what I'm-
can.
what I'm-
Yeah, that's true. Okay, let's see how this works. So, you guys, yeah, you guys, okay, yeah. You're my singlet fission material, and you guys are my nanoparticles.
Ooh, okay.
Okay, so I am light, and I hit you. Okay,
Just one.
Wait, doesn't one of them go up?
yeah, let's just do 1 goes up.
Which spin do we care which?
No.
No. Okay. Now you're a really good singlet fission material, so you undergo singlet fission really quickly.
Oh, wait.
Yeah. Oh, yeah. Perfect. Okay. Now you guys. Here, let's switch hands so you guys could. So now you guys move and you meet the nanocrystal. So now
No.
come over here.
No.
What? Yeah.
Well, the atoms got moved, right?
They're molecules, and let's pretend they're
Our
hopping.
arms can't
They're
stretch
hopping
into
to
it.
other molecules. Or you guys were just right next to each other to begin with. Let's pretend you're right. Okay, so now we transfer the triplet to
1,
the
2,
nanoparticles.
3. No. This end comes towards me.
Okay,
But
So you
that's
change
not allowed.
like this.
Well,
Fabulous.
no, well you still need you transfer the triplet, but you still should have your same number of electrons.
So I'll get the triplets now, and you'll just base.
And I just have
take-
normal.
Uh,
Okay, yours. Just do this.
Yeah, like that. You just do that. This one's good. Except your transfer your energy.
Oh.
It was confusing. Should
We
do
got
it again? We got it. Basically, we got now our two excited states over into nanocrystals.
Transfer her energy.
Oh, sorry.
Coordinate transfer.
I'm sorry. Okay.
Yeah.
You're good. You're good.
Okay, now what did nanocrystals do?
Emission.
Yeah.
No. We have to turn white first.
Oh yeah. I just got rid of all the whites. Here, you could be there. No, that doesn't work.
Oh.
Go switch right
I
here.
need a white.
Electrons
I
now.
have 2 whites.
Okay.
Okay.
So that's the magic trick.
Yeah.
I
Are you
have
doing?
2
Oh.
whites.
Oh. And then now they can
No,
run
you
like
actually
this.
need to turn black.
We don't know why, but
It's magic.
magic.
It's magic. Spin orbit coupling. That's just a word, but that's why. So the orbit is another property of the electron, right? What orbit? Or is it the electron? Yeah, together. It's just the electron has a property called orbit and a property called spin.
Alright.
And then
It's okay.
I'm giving like a really, probably my version is not accurate, but basically in the nanoparticle, those two, the energies between the two can couple. They basically can exchange energy very freely. So basically you could take some energy and split the spin from the orbit or something like that.
I don't understand because you were the photon, right?
Yeah, just,
But wasn't the
Yes,
idea
I guess
that
2
there's one
photons.
photon coming in and then there's
so you're asking why there are not two
coming out?
Stevens coming out.
I don't understand.
Well, there'd be two like half Stevens coming out, right?
Yeah, two half, so like
Smaller
one,
Stevens.
two half Stevens.
Yeah, he's taller, so he.
So
this
that
It
is
would
Shouldn't
be
there be something
Laurel
coming
and Amanda coming out.
Should we have two photons? No, I think that's basically what we're trying to make in human version, is this group of singlet fission material and nanoparticles so that we can have
Maybe we can
light
use the
doubling.
beams.
No, that's way
This is gonna end up with like 3 counts.
Yeah.
too.
There's no more general questions then.
War over tea. Wait, why can't you use only singlet fission material?
Ah, yes, the original question.
What was the question? Sorry.
The earlier question I asked and then had hints for
Oh,
and
yes,
didn't
why?
answer. Okay, so if you have
Can we see the hints again?
yeah. No.
What's the second movie?
Arrow piece.
Because I know there's Matrix and the other one is.
Whoops, not sure. Yeah, I didn't know that reference. I just looked for it. They look funny. The hoods. Here we go. So the triplet energy is half that of the singlet. Okay, so and then the ideal band gap thing. So the ideal band gap was around 1, right? So we want to absorb at 1 because at 1 we get the maximum amount of photons in and waste the least amount of energy as heat. But if we absorb at 1.1 and then undergo singlet fission, then our triplets are at half that energy. So we give up some voltage there. We don't want to do that. And we can't go higher and then take half because then we exclude a lot, right? We can't just have a singlet fission material with like energy of 2 and then half that is 1, but then we can't absorb all the stuff less than 2. So people tried just collecting the exciton, like the 2 triplets in an electrode, right? You could just have it. I mean that's the part that doesn't work. Even though they tried that anyway, but the efficiency of the transfer is really low. But this way you don't have to bother because you could. Now you can, what you said, you can't use silicon, but you can. That's exactly what you want to do. You want to have your silicon solar cell beneath it, and just the singlet fission nanoparticle layer on top. And so all the light that would normally go into the silicon solar cell, the 1.1 energy stuff, it goes through the singlet fission material because you pick the singlet fission material, so that its energy is twice that band gap. So the triplet energy of the singlet fission material matches with the one below it. So the photons come out at exactly the perfect band gap energy for the solar cell beneath.
But also, like, if you get this triplet, then it doesn't have a, like, it's not positive or negative, so it doesn't. move with the electric field.
Yeah, it doesn't.
So if you wanted to go through your cable,
But that's
there's
why
no
we're
way
that's
to
why
direct it.
that's why we're emitting it as light.
Yeah. No, but that's yeah.
That's
Because the previous question is why you can't use it for.
they could still move, but it's hard. They diffuse. They will
Yeah,
still
they
go.
diffuse, but you don't control their motion.
So what? Okay, so there's a subtle difference between the solar cells I was showing you, which are basically how inorganic solar cells work, like the silicon stuff that we're used to. Organic solar cells, they work a little different in the way that they separate
Okay.
charge. But either way, it's hard to collect the triplets.